Let's try and understand crystal field theory. Crystal field theory deals with complexes of metals and ligands. Metals essentially are d block elements, and ligands spatially are Lewis bases or negatively charged ions. Now here I have taken example of COF6, cobalt hexafluoride, 3 minus. Now here cobalt is a d block element, is a metal, and it has to have essentially empty d orbitals. Alright. Whereas fluoride F minus is Lewis base. It's negatively charged. So ligands have to be Lewis base, that is, it has to have excess of electron to donate, lone pair to donate. So ligands are the donors and cobalt are the metals are the acceptors. So here fluoride is the donor and cobalt is the acceptor. Alright. Now essentially it's the lone pairs are accepted in d orbitals of metals. Alright. So when we talk about d orbitals of metals, then we have got to just recap our knowledge about d orbitals. D orbitals, there are 5 d orbitals, which are dx square y square, where the electron cloud lies on x and y axis, dz square, this is a bit scrambled, but it's okay, dz square, where the electron cloud lies on z axis. Then we have dxy, dyz, and dzx, where the electron cloud lies in between axes. Alright, this is what we have studied. Now, what do you understand by degenerate d orbital? Degenerate d orbital means that all the orbitals, all 5 orbitals are at equivalent energy level. Alright. Now let's understand a bit about structure. Now when we talk about complexes, metal complexes, there are varieties of structures like tetrahedral, octahedral, square planar bipyramidal, trigonal bipyramidal, and so on and so forth. But what we are going to observe over here is tetrahedral structure and octahedral structure. How do we represent tetrahedral structure? In case of tetrahedral structure, what we do is we take a cube, okay, we draw a cube and we show ligands approaching from alternate corners of cube. Whatever in blue over here that you see are ligands. Alright. And in tetrahedral structure, obviously there are 4 ligands approaching this central metal atom. So these 5 lines that you see are of degenerate d orbitals before the ligands approach. Alright, so ligands in case of tetrahedral structure approach from within the axes. Whereas in case of octahedral complex, we find that the ligands approach via the axes. Alright, and the structure is represented like this for octahedral. Now I told you that here ligands are approaching via axes. So via axes means, I would say, these ligands are in direct head-on interaction with dx square, dy square orbital, and these ligands are in direct interaction with, rather head-on interaction with dz square. So owing to which this degenerate level is broken. And since it is broken, so what we observe is, so this was the degenerate level, it breaks up and gets excited and moves above the barycenter. Barycenter is where the level, energy level is for degenerate level of d orbitals. Alright, so it moves above. Now if it moves above means it's plus energy. Energy cannot be generated, alright, as per conservation of energy. So the remaining orbitals has to go down in energy level. And which are the remaining orbitals? Obviously dxy, dyz and dzx, as they are not on head-on interaction with ligands. So energy, this is negative energy, this is positive energy, this is negative energy. Alright, let's understand. That's about octahedral complex. Let's understand tetrahedral complex. In tetrahedral complex, we found that the ligands were approaching via in between the axes. Now, since ligands were approaching via in between the axes, so obviously we would expect dxy, dyz and dzx to move above the barycenter and this to move down the barycenter energy wise. Alright, so this is what happens. Now, I need to tell you one thing. These three dxy, dyz and dzx are known as T2G level, and x square, y square and dz square are known as EG level. Alright, so EG and T2G here. Alright, so here we find that T2G level goes up, EG goes down. Here we find EG goes up energy wise and T2G level goes down. Alright, that's about a bit of energy and about the structure and about how ligands approach the central metal atom and how does it affect the degenerate d orbital to give EG and T2G level. Now we would further see the actual process of conservation of energy, how this energy gained is equal to this energy lost. Alright, so following conservation of energy theory. Alright.